Okay, so the last thing we were trying to do was to estimate the condition number. And the condition number gives us an idea how invertible our matrix is. Very large condition numbers signify that the matrix is not the best matrix to invert. Okay, so if you want to compute a inverse, a way of estimating the condition number is to just say that the condition number of A, we were just about finishing this. I was going to do a proof, but we're running out of time. So the condition number of A is approximately Y star over, and this is the norm of X star, times 10 to the T. So now, where Y star happens to be approximately A inverse times R. Okay. All right, so I want to talk about two other methods for solving AX equals B. And they are the Gauss-Jacobi and Gauss-Seidel iterative methods. So let's see, determinants should have had a D, and then vector M matrix norms and condition number should have had an E, and then this can now be F. And this is the Gauss-Jacobi and Gauss-Seidel. I tended to like these when I was learning these. All right, so let's say we're given the system AX equals B. So we're going to do Gauss-Jacobi first. Okay. All right, so we have a system. Okay, so there are two assumptions that are made for this thing. All right, so two assumptions are made. On the Jacobi method. Okay, so the first one is that the system AX equals B, okay, where A is an n by n matrix, has a unique solution. So that's the first assumption. Okay, so we're looking at something that looks like A11x1 plus A12x2 plus dot 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 A1nxn equals B1, A21x1 plus A22x2 plus dot 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 plus A2n xn is equal to B2. And we're going to dot 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 all the way down to AN1 x1 plus AN2 X2 plus dot, 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 all the way up to ANN XN is equal to BN. So this is what we have, okay? And the assumption is, let me put my dots in the middle, out of there. Okay, so the assumption is that the system has a unique solution. So that's a big deal, okay? That is a big, major assumption. Okay, in other words, no point in solving the problem if I don't know it has a unique solution. It won't work for something that does not have a solution or something that has infinitely many solutions. Okay, 2, the second thing is the coefficient matrix A has no zeros on the diagonal. Okay, so that's the second major assumption. All right, so now that I have those two assumptions, all right, the idea is we're going to take, and at each stage, we're going to start with an initial guess of what we think our solution is, all right? And then we're going to solve for each thing. So in the first equation, I'm going to get x1. So let's solve. So we're going to solve for, in the first equation, we'll solve for x1. In the second equation, we'll solve for x2. So we're going to solve for xi in the ith equation. Okay, so what does that look like? So it looks like x1 is 1 over a11. And then everything on the left-hand side gives us b1 minus a12 x2 minus a13 x3 minus dot, 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 minus a1n xn. Okay, so in the second equation, we're going to get x2 is going to be 1 over a22. And I'm going to have b2 minus, and now I'm going to have a21 x1 minus a23 x3 minus dot, 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 minus a2n xn. And then I'm going to do this all the way down to the last equation and get xn is going to be 1 over ann. And then I'm going to have bn minus an1 x1 minus an2 x2 minus all the way down to an n comma n minus 1 x n minus 1. Okay, so that's down to the last one. Okay, so now what we're going to do is start with an initial guess. So our initial guess is going to look like x naught. And this is going to be x1 naught, x2 naught, all the way down to xn naught. So that is my initial guess, okay? And then I am going to compute x1 let me put the 0 on the top. Now I'll put the 1 up here. So we're going to compute x1 using these equations in the box. So let me put these in a nice box. Okay. Okay. So we're going to compute an x1 iterate, which is going to be found using equations star. Okay. And so when we do that, that will give us x1, which would be x1, 1, x1, 2, all the way down to x1, n. Okay, so then what we want to do is we want to check the relative error. So we're going to look at the norm of x0 minus x1 divided by, and I'm trying to think which one do I want to use. I guess we can use x1. Is less than some number epsilon. Okay, so if true, stop. Otherwise, compute x2. Okay. And you will continue until. Now, this method, from what I have is an algorithm. They're not doing the relative error. They're just doing the error. Oh, okay, good. I like this one. Okay, good. They do it. Until the norm between x, the kth one, minus x, k minus 1, divided by the length of xk is less than some number epsilon, and this is my tolerance. Smaller epsilon is, the longer your thing will proceed. So again, here epsilon, that's my tolerance. Okay, so this is a really nice method that works. Okay. Here is the algorithm. I don't know why it bounces around like that. That's weird. I don't know. Okay, I'm just glad it's doing what it's supposed to. Okay. So your input is your matrix A. Okay. You need to put in your vector B. And then you need to put in your X0, your guess. And your epsilon tolerance. Okay. All right, so all of that needs to be in there. And I need to tell it N how many iterations I'm willing to tolerate before I just have it stop. Okay. So first thing I'm going to do is set K. So step 1. Set K equal to 1. And with K is equal to 1, actually, for K less than or equal to N. Okay, then we're going to have 4. Step 2. K less than equal to N, we're going to have step 3. So you're going to do 4 I equal to 1 all the way up to little n. So this is my mistake. This should be capital N because that's where I want it to stop. Okay. So originally you can set you need to tell, well, it needs to know this, what little n is. Okay, little n is the size of A. Okay, so then you're going to compute xi, which is x at I, okay, is going to be equal to 1 over AII times the sum j equal to 1, j not equal to I, to n of minus a ij times x naught, that's the initial vector, at j, plus, so we're doing that sum, and then we're going to add bi at the end. Okay. Okay. Actually, that's stupid. I don't like the way they wrote it. I'm going to write it my way. Bi minus the sum I equal 1 to n. This is j. J not equal to I of aij x naught at j. Much better. I like that better. Goodness gracious, the way they wrote it was crazy. And Then we're going to have step 4. And step 4 is if the absolute value of x minus x naught is less than epsilon, then output my x1 down to xn. Okay. And then break. Okay. Step 5. Set k equal to k plus 1. Okay. And then step 6, we're going to have for I equal to 1 to n. You're going to let x0 at I equal x at I. So you're going to save your new solution. Then you can step 7, output your x, and then stop. Now, I forgot an end. Yeah. So this loop will continue this loop right here. Okay. All right. So what does that look like? We have an example. Okay. Apply Jacobi method to solve the following. 5x1 minus 2x2 plus 3x3, which is xn, is equal to -1. So here little n is equal to 3 because a is 3 by 3. Minus 3x1 plus 9x2 plus x3 is equal to 2. And then 2x1 minus x2, that can't be right. This can't be right. Oh, yes, it is. Minus 7x3 is equal to 3. I was thinking the diagonal couldn't be negative. The diagonal doesn't have to, it's okay. The diagonal can't be 0. That's the problem. Okay, so now we rewrite it. And we get x1 is equal to 1/5 of -1 minus plus 2x2 minus 3x3. Then we get x2 is equal to -1/9 of 2 okay, that's a problem. This is a plus. So that's not, I'm trying to figure out why my answer is not looking like theirs. Okay, 2 plus 3x1 minus x3. Okay, now that looks right. And then x3, it's divided by -7. So it's -1/7 times 3 minus 2x1 plus x2. Okay. So let's choose our first guess to be something simple, 0, 0, 0. Okay. So if I do that, so at the first iteration, I get x1, 1 is equal to -0.200. X1, the second element, is 1/9, which is 0.222. Actually, that's 2/9. Yes. And then x3 of the first iterate becomes -3/7 minus 0.429. Okay, so that's my first guess. Okay, so now I'm going to put those numbers.
Excuse me.
Yes.
The first guess, like you just choose anything.
Say that again.
I mean the first guess.
We just guess. You can pick whatever you want.
Oh, okay.
Yes, I just picked 0, 0, 0.
All right.
Okay, and so it gave me this answer. Okay. And so now I will take those x1. So now we take this right here and we plug it. Okay, we don't. And we plug it back into here to get x2. Okay.
Okay.
So the second iteration, you're going to get x1. So oh, wrong thing. So the second iteration is going to be x2, 1 is going to be 1/5 -1 plus 2 times x2, which was 0.222 minus 3 times -0.429. And that turns out to be 0.146. And then x2, the second one, turns out to be 1/9 times 2 plus 3 times negative 0.200, because that's the first one, minus x3. So minus a negative 0.429. And that turns out to be 0.203. And then x3 of the second one is negative 1/7 times 3 minus x1, which is negative 0.200, plus, oh, it's 2 times that. x1, negative 0.200 plus x2, and x2 was 0.222. And that turns out to be negative 0.517. Okay. And then you just continue. So we continue the algorithm. So at the third iteration, you get x31 turns out to be 0.192, x32 turns out to be 0.328, and then x3 turns out to be negative 0.416. Okay. All right, so now you can actually compute this in matrix form. Okay.
Okay. The value for S1, S2, S3.
Where?
The first one, X1 of 1, S2 of 1. Yes. How did it? Okay.
How did we get those?
Mm-hmm.
We put 0 in for everything. So I just get negative 1/5, which is this one. I get 2/9 because that's 0. So I get this one. And I get negative 3/7. So I got that one because everything else was 0.
Okay. Yeah, that's okay.
And then I actually showed you how I got the second one.
Mm-hmm.
Okay.
Yeah.
All right. So now the Jacobi method, I gave you the algorithm. Okay. So that's how you can compute it. So you can, with MATLAB, it's nice to be, so with MATLAB, this is how you can compute it. Okay, so with MATLAB, again, we're solving AX equals B. Okay. So you want to take and you want to split A into these matrices, okay? So A is going to be the first piece, which only contains the diagonal. A11, A1, A22, A22, ANN. That's the diagonal. Everything else is 0. Okay. Then you're going to subtract off the lower part. So then we're going to get 0. So we're going to get 0. And then I'm going to get negative A21, negative A22. I'm sorry, A31 down to AN1. And then I'm going to get negative A. Nope. I want everything just underneath the diagonal. So the diagonal is 0. So this should be negative A32, 0, all the way down to negative A N N. Nope. A N N is not there. It's the second to the last one, which should be A N N minus 1, 0. And then all of that is 0. And then I'm going to subtract off the top piece. So the top piece is going to be negative A12. Nope, there should be a 0 in that column. There should be zeros all the way down the diagonal, and these should have zeros. So okay, this is the exact opposite. This should be negative A12, negative A13, all over negative A1N, and then 0, and then 0, 0, and this should be negative A23. And then the last 0 down here, all of this is 0, and this one should be AN minus 1N, and it's negative. Okay. So now the first matrix that one I'm calling D. So A is going to be D minus. The second one I'm calling L. And the third one I'm calling U. Okay. D, L, U. Okay. So now we end up with AX equals B becomes D minus L minus U times X is equal to B. Okay. So now we can solve for D. D times X is now going to be L plus U times X plus B. All right. Now remember, D, the A has no zeros on the diagonal. So since AKK does not equal 0 for any K, D inverse exists. And D inverse is just a matrix 1 over A11, 1 over A22, 1 over A33, 1 down to 1 over ANN. Where this is 0 and this is 0. Okay. All right. So X turns out to equal D inverse times L plus U times X plus B. All right. So then you get, D inverse times B. I forgot to multiply B by D inverse. D inverse times B. Okay, so if you let T now equal L plus U, and you let the vector C equal D inverse B, you now have X is equal to D inverse times T X plus C. Okay. I'm sorry. Put D inverse inside of here. Just put D inverse times L plus U. Okay. So then there's no D inverse. So now it's just Tx plus C. And so here's the iteration. So for MATLAB, the iterative scheme is X K plus 1 is going to equal T times X K plus C. And again, we keep going to the length of X K plus 1 minus X K divided by the length of X K plus 1 is less than epsilon. So it's beautiful in MATLAB. Okay. All right. So that is the Gauss-Jacobi iterative scheme. It works very nice. Again, the two criteria, you have to know that the solution exists, a unique solution, and you also need to know that the zeros on the diagonal do not exist. Okay, so then Gauss got another graduate student, okay, named Seidel. And so Gauss wanted to improve on the Gauss-Jacobi iteration. And so they came up with the Gauss-Seidel method. So now we're going to do that. And we're going to assume the same two assumptions. Okay. Okay. So now we have the Gauss-Seidel. Now the difference between the Gauss Jacobi and the Gauss-Seidel is that with the Gauss-Jacobi, we calculated x1, x2, x3, x4, x5, all the way down to xn, and we stopped, and then we went and calculated the next vector, okay? The difference with the Gauss-Seidel method is as you compute a new one, you put the new one in the equation and don't wait to compute the next one, okay? So let's take this scheme back here that we had. Okay. So again, we have the same two criteria. Okay. Same assumptions. So the same assumptions are made as in the Jacobi method. Okay, so system has a unique solution and the coefficient matrix has no zeros. Okay, so now I'm going to write this and call this equation double star. And I'm going to modify it. Okay, so that's irritating, but that's okay. So we are going to solve for the ith equation, xi in the ith equation, but, all right, we are not going to wait to solve for xi plus 1. Okay, so we solve for xi in the xi equation. But we do not, I hate the word don't, wait to solve for all the xi's at the k plus first level. Okay, so what do? We start off with x1. Let me see here. For some reason, it's acting kind of funky. Oh no, it did it. That's what I wanted to do. Okay, good. Undo for a moment. Let me get rid of my green bar. Let's get rid of my little green box here. Okay. So the first equation stays the same. So this is at k plus 1, we solved that. But now, when we go, and all of these are at k. Okay, but now when we go to solve for x2 at k plus 1, we're actually going to stick in x1 at k plus 1. And then this is still at k, and this is still at k. Okay. So then when we solve for x3 at k plus 1, it's going to be 1 over a33 times b3 minus a31 x1 at k plus 1 minus a32 x2 at k plus 1, and then minus a34 x4, sorry, x4 at k, because we haven't updated that yet, all the way down to a3n xk at n. Okay. So then by the time we get to the last one, this one at k plus 1, everything's known. So this is bn an1 x1 at k plus 1 minus an2 x2 at k plus 1 minus dot 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 minus a n minus 1 x n minus 1 at k plus 1. Okay. So this is the new algorithm. So this one, as you find a new iterate, you use it immediately. Okay, we don't wait. So this one is equation double star. Okay. So again, we start with an x0. X0 to x0 n. And then we continue with to compute the error. Ooh. Okay. So since we for the most part are using Maple, I'm going to give you the matrix form of the Gauss-Seidel method. Did I say Maple? I mean MATLAB. Okay, so with MATLAB, you have the same A is equal to D minus L minus U, same as before. Okay, so now we have D minus L times X at K plus 1 is equal to U times X at K plus B. So therefore, X hold on 1 second, please. Wow, this is just great.
Excuse me, Takano, I cannot hear you. Are you talking?
Okay, I apologize. Okay, so now let me say this again. So x at k plus 1 is equal to d minus L inverse times u x at k plus d minus L inverse times b. Okay, so now we're going to let T, I'm gonna put G so you know that that stands for Gauss, is equal to D minus L inverse times U. And we're going to let C, Gauss, be D minus L inverse B. Okay, and so therefore we get X at K plus 1 is equal to TG times X at K plus CG vector. And again, we do this with the same stopping criteria. Okay. All right. Now the rate of convergence for this depends on the spectral radius. And the spectral radius is the largest eigenvalue of the matrix. So that is how we have to compute this. I'm trying to see, I will give you these theorems, but unfortunately, I'm not going to be able to prove them. I just don't have the time. Okay, so, yep. Okay. So let me give you convergence theorems of the of the iteration methods. Okay. All right. So, so let's consider the convergence, consider the method. Okay, so it's either one. So we have T. So no, we don't. We have X, K plus 1 is equal to T times X at K plus C. Okay, so first is a lemma that says if the spectral radius satisfies, that's rho of T, that's the spectral radius, is less than 1, then identity minus T inverse exists. And you can write the identity minus T inverse as 1 plus T plus T squared. This is a geometric series plus dot, dot, dot. And that equals the sum J equals 0 to infinity of T to the J. Okay. We have a theorem that says for any x0, that's an element of Rn. The sequence defined by that is x, k, that sequence for which x, k plus 1 is equal to t times x, k plus c converges to the unique solution if and only if the spectral radius of t is less than 1. And then lastly, corollary, if the norm of t is less than 1 for any natural matrix norm, that includes the spectral radius, the, remember we had the Frobenius norm, we had all those, and C which is element of Rn, then the sequence defined by xk plus 1 equal to t times xk plus c converges for any x naught to an element of R to a vector we're calling capital X, which is an element R, and the following error bounds hold. Okay, so the first one is the norm of the solution minus any iterate xk is going to be less than or equal to the norm of t raised to the k power times the difference between x0 and the final iterate x. And number 2, the distance between x minus x, the kth one, is less than or equal to the length of t to the k divided by 1 minus the norm of t times the absolute value of x1. Okay. And then lastly, the theorem it says if A is strictly diagonally dominant. Then for any choice X naught, both Gauss-Jacobi and Gauss-Seidel give sequences of X, K. All right, that converge to the unique solution AX. Okay. All righty. We now are at the place where we have one last topic we have to do. Now, here's the deal. I don't think we have enough time to complete it, but we have to complete it. And we did miss one lecture, so I am requesting that if you have the time on Thursday to extend the lecture, if you don't have another class right afterwards, I'm asking, can we extend the lecture to complete the last topic for Thursday?
Me and Uchina, we have class on 1:30 after that.
We have class at 1:30. How about 3 o'clock?
Oh,
I have meeting.
yeah, Uchina has meeting.
Okay, let's see. When can we do this last stuff? You guys have time on Friday?
I'm sorry, on Friday we have the group meeting too.
Okay, then I will. I think I might scan the notes and then we'll just go through them. I'm not sure what I gotta do. And I don't know. I need you to learn the power method, but I don't know if we're gonna have time to get through the whole power method. If not, then we just don't, and I'm not gonna stress about it. Okay, so we'll do what we can on Thursday. And what we don't get to, I'm not gonna stress about because I just can't.
Okay.
Okay.
All right, yeah, I